In question 4, we are looking at solving a definite integral. And we're going to solve it in two ways. One, we're going to construct a Riemann sum and use that to compute the definite integral. And the second way we're going to solve the definite integral is by using the fundamental theorem of calculus. So first, what we need to do is we need to set up the Riemann sum formula for this expression. And those in my class know I like to create a little pie shape to remind myself of what it is, where I have delta, or I have n equals n, because I'm using n rectangles. A equals 0 in this case, b equals 2, f of x equals 4 minus x squared. So now that I have my pieces, I want to compute what delta x is. This is b minus a over n, capital N, which equals 2 minus 0 over little n, which equals 2 over little n. Now I want to compute what xk star is. Oh, well, it turns out they gave me xk star is 2k minus 1 over n. So this allows me to compute f of xk star, which equals f of 2k minus 1 over n, which equals 4 minus 2k minus 1 all over n, which equals 4 all squared, which equals 4 minus 4k minus 1 squared over n, which equals 4 minus 4k squared plus 8k minus 4 all over, oh, there's an n squared on the bottom, all over n squared. And we have our Riemann sum. The Riemann sum, Rn, equals the sum of I equals 1 to n f of xk star delta x. So this equals the sum of, I guess this is k equaling 1 to n. So this is k equaling 1 to n of, now it's 4 minus 4k squared plus 8k minus 4 all over, this should be this here should be a minus plus minus plus over n squared, all times 2 over n. And this is my Riemann sum. Okay. Now in the second expression, I'm going to expand this Riemann sum and use these formulas. And I'm going to take the limit of the Riemann sum as n goes to infinity. But I'm going to kind of finish here and get into what's called closed form by distributing and solving. So this equals the sum of k equaling 1 to n of 4 of 8 over n minus the sum of k equaling 1 to n of 8k squared over n cubed plus the sum k equaling 1 to n 16k over n cubed minus the sum k equaling 1 to n of 8 over n cubed. And now I would like to use these formulas to further simplify this expression. So I'm going to take these expressions and I'm going to use these formulas to simplify them. And before using them, I'm actually going to rewrite it in a slightly nicer way. So this is going to equal 8 over n sum of k equaling 1 to n 1 minus 8 over n cubed sum of k equaling 1 to n k squared plus the sum of k equaling 1 to n, or plus 16 over n cubed, k equaling 1 to n of k, minus 8 over n cubed, sum of k equaling 1 to n of 1. And now here, each of these pieces, you'll note I can just use my rule. So this gives me 8 over n times n minus 8 over n squared times n plus 1, 2n plus 1 over 6. This is n cubed, plus 16 over n cubed, n plus 1 over 2, minus 8 over n cubed times n. And now that is Rn in closed form. Now, going into our expression down here, really everything up to this point is starting to solve b. But what b wants us to do is it wants to take us to take the limit as n goes to infinity of this expression of 8 minus 4, or I'll simplify the next step. 8 over n times n minus 8 over n cubed, n plus 1, 2n plus 1 over 6, plus 16 over n cubed, n plus 1 over 2, minus 8 over n cubed times n. This equals the limit as n approaches infinity of 8 minus 4 over 6, n plus 1, 2n plus 1, all over n squared minus 16, or minus 8 n plus 1 over n cubed. This is a plus, and then minus 8 over n squared. Now here, I'm going to leave it as a little exercise for you guys to work through, but you can expand this numerator and expand this numerator and expand this. You can show that this term goes to 0, this term goes to 0, this term goes to, oh, this should be a 3. This term goes to 8 over 3. And then we have our term 8, so it equals 8 minus 8 over 3, which equals 24 over 3 minus 8 over 3, which equals 16 over 3. And that's our solution. And in part C, it wants us to verify this using the fundamental theorem of calculus. So here, we're going to take the integral 0 to 2 of 4 minus x squared dx, which equals 4x minus x cubed, evaluated at x equals 0 to 2, which equals 4 times 2 minus, oh, that's x cubed over 3, 2 cubed over 3 minus, that's my first function plugging in 2, minus 4 times 0 minus 0 cubed over 3, which equals 8 minus 8 over 3 minus 0, which equals 24 over 3 minus 8 over 3, which equals 16 over 3. And we have our same solution. Now we have two indefinite integrals we'd like to calculate in Q6. So here, the trick is we need to do a U-substitution in order to solve these. So first we're going to compute the definite integral. And so on the aside, I'm going to do the definite integral for sine of x e to the cos of x dx. And u equals cos x. This is my guess. Then du by dx is minus sine of x and 1 over minus sine x du by dx equals 1. So this equals the integral of sine of x over minus sine x e to the cos x du by dx which equals minus the integral of e to the u du by dx which equals e to the minus e to the u c, which equals minus e to the cos x plus c. That's my improper integral. So this equals minus e to the cos of x evaluated at x equals 0 to pi. So this equals minus e to the cos pi minus e to the cos of 0. Now, cos of pi is going to be minus 1. So this equals minus e to the minus 1 minus e, and cos of 0 is 1. So 1. So it's going to be equal to e minus e to 1 over e, which if we do a common denominator, we get e squared minus 1 over e, which is e minus 1, e plus 1 all over e. We'd expect you to get to this type of step. In part B, we have a substitution, and the substitution is where we make the ugly from the inside go to the outside. Again, we need to solve the indefinite integral first, and then use our fundamental theorem of calculus 1. So u equals x plus 1. I'm going to do two things. I'm going to solve this by then updating the bounds of my integral. So if I let u equal u plus 1, then u equals x plus 1, then u of 2 equals 2 plus 1 equals 3, and u of 5 equals 5 plus 1 equals 6. Du by dx equals 1, and this also implies that x equals u minus 1. So this equals the integral from 3 to 6 of u minus 1 u to the 1/2 du. And here, the way I've done it, I don't need to convert back. So this equals the integral from 3 to 6 of u to the 3/2 minus u to the 1/2 du, which equals u to the 5/2 over 5/2 minus u to the 3/2 over 3/2, evaluated at x equals 3 to 6. This is equal to 2/5 6 to the 5 over 2 minus 2/3 6 to the 3/2 minus 2/5 3 to the 5/2 plus 2/3 times 3 to the 3/2. And this is a 5/2. And this is my solution.